Look up into the vast, clear darkness of an autumn night sky. Out there, a chilling process is underway. A structure of almost inconceivable scale, 2.5 million years of light travel away from you, is growing. It is a cosmic leviathan, and scientists have just realized its true dimensions are far greater and far more unsettling than we ever imagined. The most mind-altering fact is not its size, but its invisibility. This object spans a patch of sky more than 6 times wider than the full moon, yet your eyes glide right over it, completely oblivious to the monster hiding in plain sight. It is the Andromeda Galaxy, our nearest major galactic neighbor, and its invisible presence is already reshaping our understanding of the universe and our own ultimate fate. If you could see it, if its light were just a fraction more concentrated, it would be the undisputed queen of the night sky. It wouldn't be a faint smudge. It would be a majestic, glowing disk of light so vast it would make every constellation around it seem insignificant. Its apparent size would dwarf the Big Dipper, stretching across an area of the sky so wide you'd have to turn your head to take it all in. If you enjoy diving into cosmic mysteries, hit that like button. Prepare yourselves and let's dive in. For over a millennium, we have been staring at it, completely underestimating its grandeur. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi cataloged it in his Book of Fixed Stars, describing it simply as a small cloud. For centuries that followed, that's all it was to us. A nebulous patch, a curious cosmic vapor thought to exist within our own Milky Way galaxy. No one suspected they were looking at a separate, colossal island of 1 trillion stars, an empire of suns and worlds rivaling our own, separated from us by an almost unimaginable gulf of intergalactic space. The paradigm shift began not by seeing more, but by measuring differently. The crucial concept is angular size, a measure of how much of your field of view an object occupies. For context, if you extend your arm, your little finger's width is about 1 degree of the sky. The full moon is half a degree. From end to end, the famous Big Dipper asterism spans about 25 degrees. Modern instruments, far more sensitive than the human eye, revealed Andromeda's stellar disk to have an angular diameter of over 3 degrees. This presents a profound paradox. How can something 6 times the angular width of the moon be so difficult to see? The answer lies in a crucial but often overlooked property: surface brightness. Imagine you have a can of paint. If you use it to paint a small dot on a wall, that dot will be bright, opaque, and obvious. Now take that same amount of paint and try to spread it over an entire room. The color would be so thin, so diffuse, that it would become a transparent, barely perceptible wash. This is precisely the case with Andromeda. Its 1 trillion stars generate a colossal amount of light, but that light is spread across an immense area of the sky. Each individual point within its disk is incredibly faint. Our eyes, evolved to detect concentrated points of light like stars or the nearby moon, simply cannot gather enough photons from any single part of Andromeda's sprawling disk to register a clear image. The galaxy's light is there, raining down on us constantly, but it is so diluted by its own scale that it vanishes into the faint background glow of the night. To truly perceive it, astronomers use technology that does what our eyes cannot. They gather light over time. Using massive telescopes and specialized digital cameras, they can take long exposure photographs, allowing photons from Andromeda to accumulate on a sensor for hours on end. Slowly, painstakingly, an image is built. The bright, dense galactic core materializes first, the very same fuzzy patch seen by Al-Sufi 1,000 years ago. But as more light is gathered, the galaxy's true form emerges. Elegant, ghostly spiral arms sweep outwards, traced by the faint glow of billions of stars, revealing a structure of breathtaking scale and complexity. The sheer physical size implied by these measurements is staggering. Our moon is about 384,400 kilometers away, a stone's throw in cosmic terms. Andromeda is 2.537 million light-years distant. A single light-year is the distance light travels in a year, which is approximately 9.46 trillion kilometers, to appear 6 times wider than the moon from 60 quadrillion times farther away. Andromeda's physical diameter must defy easy comprehension. Let's try another analogy. Hold a standard basketball at arm's length. It covers about 2 full moons worth of the sky. To match the angular width of Andromeda's visible disk, you would need to line up 3 of these basketballs side by side. Yet this entire structure, this cosmic metropolis containing 1 trillion suns and likely trillions more planets, is compressed by distance into a faint blur that most of the 8 billion people on Earth have never knowingly seen. For decades, this was the accepted image of Andromeda, a colossal spiral, larger than our Milky Way, but with a well-defined boundary where its starlight seemed to end. Textbooks confidently stated its stellar disk was around 120,000 light-years in diameter, only slightly larger than our own. We thought we understood its scale. We were catastrophically wrong. Even this astounding picture, assembled over decades of observation, was just a prelude. The visible disk, the part of the galaxy that glows, represents only the innermost, most concentrated fraction of the true structure. The real Andromeda is a monster of a completely different order of magnitude, with an invisible architecture that extends far beyond its stars. The most shocking discoveries were yet to come, revealing a galaxy so vast that its outer limits are already touching our own. For the majority of the 20th century, the scientific consensus on Andromeda's size was firm, yet fundamentally flawed. Astronomy textbooks and research papers quoted a diameter for its stellar disk in the range of 70,000 to 120,000 light-years. This figure was not a guess. It was based on the best available observational evidence of the time. Scientists determined this boundary by pointing their telescopes at the galaxy and measuring where the density of its stars, and thus its light, appeared to drop off into the blackness of intergalactic space. The edge of a galaxy was, by a practical and seemingly logical definition, the point at which our instruments could no longer detect its starlight. Beyond this faint perimeter was assumed to be nothing but the cold, empty void between galaxies. It was like trying to map the full extent of a continent by only looking at its brightly lit cities at night, assuming the dark countryside between them was simply non-existent land. The reality was that Andromeda's stellar empire extended far beyond what our photographic plates could see. The revolution in our understanding came not from a more powerful camera, but from a more sophisticated technique. Instead of just looking at the brightness of stars, a team of astronomers, led by Scott Chapman, decided to measure their motion. Their work, conducted using the powerful 10-meter twin Keck telescopes in Hawaii, targeted not the bright, obvious stars of the inner disk, but the far-flung, incredibly faint individual stars scattered across a region previously dismissed as the halo. This halo was thought to be a chaotic sphere of stars gravitationally bound to Andromeda, but not part of its organized, rotating disk. These were presumed to be stragglers, the orphaned stars of smaller galaxies that Andromeda had cannibalized over billions of years, now moving on random, disorganized orbits. The team meticulously measured the properties of approximately 3,000 of these faint stars, a painstakingly small sample given the galaxy's total population of 1 trillion. But what they were looking for wasn't a census, it was a pattern. The key measurement was the star's velocity relative to the galaxy. Every star in a galaxy is in constant motion, held in its orbit by the colossal gravitational pull of the galaxy's total mass, most of which is invisible dark matter. By measuring a star's speed and direction, you can determine the nature of its orbit. Stars within a galaxy's rotating disk all move in a coherent, organized fashion, like horses on a carousel. They all orbit in the same direction, within the same flat plane. Their speeds change predictably with distance from the galactic center, but the overall pattern is one of order. Halo stars, by contrast, should behave like a swarm of angry bees, moving in all directions, some plunging up through the disk, others down, some orbiting forwards, others backwards. Their velocities should appear random and chaotic. The team used a technique called spectroscopy to dissect the light from each of their 3,000 target stars. By looking for the Doppler shift in the star's light, the subtle stretching or compressing of light waves due to its motion toward or away from us, they could calculate its line-of-sight velocity with incredible precision. When they plotted these velocities against the star's positions on the sky, the data delivered a profound shock. These stars, located far beyond the previously accepted edge of the galaxy, were not moving randomly. A significant population of them displayed the clear, unmistakable signature of disk rotation. They were moving in concert, orbiting Andromeda's center in the same plane and in the same direction as the inner, visible disk. The implication was immediate and irrefutable. These were not halo stars at all. They were an integral part of the stellar disk itself. The disk did not simply end where its light grew faint. It continued outward, a vast, sparsely populated but dynamically connected extension of the main galaxy. This single discovery forced a complete and radical recalculation of Andromeda's size. The stellar disk wasn't 120,000 light-years across. It was a colossal 220,000 light-years in diameter. This tripled its previously estimated size. To put this new measurement into perspective, consider our own Milky Way. Our galaxy's stellar disk is approximately 100,000 light-years across. For a long time, we thought of Andromeda as our slightly bigger sibling, perhaps 20 to 30% larger. This new data revealed it to be a true giant. Its disk doesn't just span twice the diameter of the Milky Way's. It covers more than 4 times the area. The volume of space occupied by its stellar population is vastly greater than our own. This wasn't a minor correction. It was a fundamental recalibration of our place in the local universe. We live next door to a galaxy that absolutely dwarfs our own. This extended disk is a strange and messy place. Unlike the elegant, well-defined spiral arms of the inner galaxy, the outer regions are clumpy and irregular. The stars are not arranged in smooth, flowing streams, but are gathered into loose associations and overdense patches. This very messiness provided another profound clue. Computer simulations of galaxy formation showed that such a turbulent, extended outer disk could not form through quiet, isolated evolution. It could only be the result of violence, the aftermath of cosmic collisions. This arc is a cosmic scar from shattered galaxies torn apart by Andromeda. The revelation of the disk's true size sent ripples through nearly every field of astrophysics. All calculations of Andromeda's mass, its star formation history, its total stellar population, and the distribution of its dark matter had been based on the old, incorrect size. Every one of those models was now obsolete. The scientific community had to go back to the drawing board, armed with the knowledge that Andromeda was far larger, more massive, and had a much more violent history than we had ever conceived. Yet, as monumental as this discovery was, it only described the galaxy's stellar component, the part that shines. The true boundary of Andromeda's domain, the full extent of its gravitational and physical influence, lay in a realm that is completely invisible, a structure whose discovery would make even this new, larger disk seem small in comparison. A galaxy does not end where its stars fade into darkness. Like a planet with an atmosphere, every major galaxy, including our own, is enveloped in an immense invisible shell of gas. This structure, known as the circumgalactic medium, or more simply the halo, extends far beyond the shimmering stellar disk. In the case of Andromeda, this gaseous halo is the true monster, a structure so vast and massive that it fundamentally rewrites the definition of what a galaxy is, and has led to the most startling revelation of all. The collision with our own galaxy has, in a way, already begun. This halo is composed almost entirely of the simplest elements forged in the Big Bang: hydrogen and helium. However, this is not the dense, cold gas you find in the star-forming nurseries of the spiral arms. The halo gas is extraordinarily rarefied and searingly hot. To visualize its density, imagine taking a single grain of sugar and dispersing its individual molecules throughout a volume larger than the entire planet Earth. In the near-perfect vacuum of deep space, you might find a few atoms per cubic centimeter. In Andromeda's halo, the density can drop to less than 1 atom every 10 cubic centimeters. This extreme thinness, combined with its high temperature, makes the halo completely invisible to conventional telescopes. It emits virtually no light of its own, nor is it dense enough to block the light from objects behind it in any obvious way. It is a ghost, a phantom structure whose existence was theorized for decades, but which remained unmeasurable. The breakthrough for mapping this invisible realm came from a truly ingenious method, using some of the most luminous and distant objects in the entire universe as cosmic flashlights: quasars. A quasar, short for quasi-stellar object, is the intensely brilliant core of a very distant young galaxy. They are powered by supermassive black holes, billions of times the mass of our sun, which are actively feasting on surrounding gas and stars. As matter spirals into the black hole's maw, it forms an accretion disk that is heated by friction and gravitational forces to millions of degrees, causing it to blaze with the light of 1 trillion stars from a region no larger than our solar system. A single bright quasar can outshine its entire host galaxy, making it detectable across billions of light years. Their immense distance is the key. For us to see a quasar, its light must travel for eons across the cosmos, and on its long journey to Earth, it must pass through anything and everything that lies in its path. This includes the invisible halos of intervening galaxies like Andromeda. While the halo gas is too thin to block light outright, its constituent atoms can do something very specific. They absorb light at precise, characteristic wavelengths. An atom of hydrogen will only absorb photons with the exact amount of energy needed to kick its electron into a higher energy state. The same is true for atoms of oxygen, carbon, or silicon, each with its own unique spectral fingerprint. When the smooth, continuous spectrum of light from a distant quasar passes through Andromeda's halo, the atoms within that gas steal photons at their specific frequencies, leaving behind a pattern of dark, narrow gaps in the rainbow of light. These are called absorption lines. By capturing the quasar's light with a telescope and splitting it into a detailed spectrum using an instrument called a spectrograph, astronomers can read this cosmic barcode. The presence and pattern of absorption lines tell them exactly what elements the light passed through, and the strength of those lines reveals the density of the gas. It is the cosmic equivalent of analyzing the composition of a fog by observing how it filters the light from a distant street lamp. This is precisely what a team of astronomers did using the Hubble Space Telescope. Their program, codenamed Project Amiga, absorption map of ionized gas in Andromeda, was a monumental effort. They identified 43 quasars whose positions on the sky placed them directly behind Andromeda's halo from our point of view. Each of these 43 quasars provided a different line of sight, a different core sample drilled through the invisible gas cloud. Some lines of sight passed close to the stellar disk through the denser inner halo. Others pierced the more remote outer regions, hundreds of thousands of light years away from the visible galaxy. By systematically analyzing the spectrum of every single one of these quasars, they could begin to build a three-dimensional map of the halo's structure, density, and extent. The results, published by a team led by Nicholas Lenner and J. Christopher Hauck, were nothing short of staggering. Previous, less comprehensive studies using just a handful of quasars had hinted that the halo might extend a few 100,000 light years. The Project Amiga map revealed the jaw-dropping truth. The halo of Andromeda stretches a staggering 1.3 million light years from its center in our direction. That is more than halfway to the Milky Way. In other directions, away from our galaxy's influence, it extends even farther, with some tendrils of gas reaching out to a mind-boggling 2 million light years. Let's pause to absorb that scale. If our eyes were sensitive enough to see this halo of ionized gas, it would be the largest and most dominant feature in our night sky. It would appear as a colossal, ghostly sphere, spanning an area more than 100 times larger than the full moon. Its angular width would be 3 times that of the Big Dipper. Every time you looked up, this immense structure would loom over you, stretching across a huge portion of the celestial sphere. But the most profound implication was not just the halo's size, but what its mass represented. By measuring the absorption strength, the astronomers could calculate the total amount of matter contained within this invisible sphere. Their conservative estimate was that the halo contains the mass equivalent of 500 billion stars like our Sun. That means the invisible gas cloud surrounding Andromeda contains at least half as much mass as all 1 trillion stars in the visible galaxy combined. Andromeda is not just a disk of stars. It is a disk of stars embedded within a far larger, far more massive sphere of gas. The stellar disk is merely the yolk in a colossal cosmic egg. This discovery forced a complete reevaluation of what a galaxy's size even means. The visible portion is a mere 220,000 light-years across. But the region where Andromeda's gravity reigns supreme, its true sphere of influence, extends 10 times farther. By any meaningful physical definition, The galaxy is an order of magnitude larger than decades of research had led us to believe. And this led to the most unsettling revelation of all. The 2 million light-year measurement is not just a number. It is a boundary that delineates the absolute edge of Andromeda's dominion. This is the frontier where the galaxy's influence finally succumbs to the vast emptiness of intergalactic space. The discovery that this boundary was not a perfect sphere, but an asymmetric, distorted envelope, provided deep insights into the galaxy's violent life history. It is a structure shaped by billions of years of cosmic fireworks. The team behind Project Omega constructed their three-dimensional model by meticulously comparing the absorption line data from all 43 background quasars. Each quasar provided a single data point on a vast map. Quasars, whose light passed closer to Andromeda's disk, showed strong, complex absorption features, indicating a journey through dense, turbulent gas. Those on sightlines passing through the outer reaches showed weaker, simpler absorption. By piecing together these 43 core samples, a picture of the halo's overall shape emerged. It was not a smooth, uniform ball of gas. Instead, it was lopsided, with vast plumes and tendrils of hot, ionized gas extending much farther in some directions than others, reaching that ultimate 2 million light-year limit. The cause of this asymmetry is the relentless, explosive power of supernova. When a star far more massive than our Sun exhausts its nuclear fuel, it doesn't fade away quietly. It collapses under its own gravity and then rebounds in a cataclysmic explosion, for a brief time outshining its entire galaxy. These explosions are the galaxy's primary engines of change. They don't just destroy the star, they blast its outer layers and any surrounding interstellar gas into space at speeds that can exceed 10,000 kilometers per second. Within the dense environment of the galactic disk, this ejected material, known as ejecta, quickly collides with other gas clouds and slows down, its energy dissipating locally. However, some of this material is blasted upwards or downwards, perpendicular to the flat plane of the disk. In these directions, there is far less gas to impede its progress. This superheated, fast-moving gas can escape the disk entirely, creating what astronomers call a galactic fountain. This escaping gas is incredibly hot, with temperatures soaring to millions of degrees Celsius. At these temperatures, the atoms are stripped of their electrons, creating a plasma of bare atomic nuclei and free-floating electrons. This ionized plasma continues to expand outwards, driven by its own immense thermal pressure and the continuous push from subsequent supernovae exploding in the disk below. Over billions of years, countless generations of massive stars have lived, died, and contributed to this process. Plume after plume of hot, metal-enriched gas has been driven out of the disk, building up an extended, layered atmosphere around the galaxy. The 2 million light-year boundary marks the point where this process finally runs out of steam. At this vast distance, the ejected gas has expanded and cooled enough that its outward pressure is no longer dominant. It finally merges with the incredibly tenuous intergalactic medium, the wispy vapor of primordial hydrogen and helium that fills the vast voids between galaxies. At this frontier, Andromeda's gravitational pull, while still present, becomes too feeble to retain this distant material, and the gas either escapes into the void or settles into the shared gravitational well of the local group of galaxies. This vast, structured halo is a fossil record. It contains the chemical and dynamical history of Andromeda's entire life. The varying densities trace ancient waves of star formation when more supernovae were erupting and driving more powerful outflows. The chemical composition of the gas, rich in elements like oxygen and carbon, is a direct record of the types of stars that have exploded over the eons. And crucially, the halo's shape and structure also preserve the scars of ancient collisions with smaller galaxies, which would have disrupted the gas and created asymmetries. But the most profound discovery from this mapping project came from its layered nature. The data revealed that the halo isn't a single uniform cloud. It has a distinct double shell structure, like two nested Russian dolls. The inner shell extends out to about 500,000 light-years from the galactic center. This region is complex, turbulent, and dynamic. Gas velocities here are all over the place, with some gas flowing outwards, pushed by recent supernovae, and other gas cooling and raining back down towards the disk. Its chemical composition is also patchy, reflecting fresh contamination from the most recent generation of exploding stars. This is the active, weather-bearing layer of the galactic atmosphere. Beyond this, a second, much larger outer shell begins. This outer region, which extends all the way to the 2 million light-year boundary, is far smoother, hotter, and more uniform. The gas here represents older material, ejected hundreds of millions, or even billions of years ago. The turbulence from its initial expulsion has had time to settle, and the gas has mixed more thoroughly. It's a more ancient, quiescent layer, representing the long-term accumulation of material over cosmic history. The existence of this double shell architecture was a complete surprise. No theoretical models of galaxy formation had predicted such a distinct layered structure. It suggests our understanding of how supernova energy couples with halo gas is incomplete. But the most immediate and startling conclusion came from a simple piece of arithmetic. The distance from the center of Andromeda to the center of the Milky Way is approximately 2.5 million light-years. If Andromeda's halo extends 2 million light-years in some directions, and at least 1.3 million light-years in our direction, and if our own Milky Way has a similarly massive halo extending outwards to meet it, then the two halos cannot be separate. They must be overlapping. A new, terrifyingly simple realization dawned on the researchers. They were not watching two distinct galaxies hurtling toward each other through empty space. They were witnessing two galaxies whose atmospheres had already made contact. The collision has already begun. This is not the future prophecy it has been for decades, but a present-day reality. It's not the spectacular, star-shredding crash of galactic disks that will dominate headlines billions of years from now. Instead, it is something far more subtle, yet profoundly significant. A gentle, silent intermingling of the two largest structures in our local universe. Right now, in the dark, cold expanse between the two galaxies, the diffuse outer atmospheres of the Milky Way and Andromeda are touching, pressing against each other, and beginning to mix. This is the first point of contact, the opening act in a multi-billion-year cosmic merger. Scientists confirmed this startling reality by scrutinizing the properties of the gas at the very edge of Andromeda's influence, in the direction of our own galaxy. When two clouds of gas meet in space, they don't simply pass through each other like ghosts. They interact. The zone of contact becomes a region of compression, where the density and temperature of the gas increase as the two fronts push against one another. This shock front, or boundary layer, should also exhibit unique velocity signatures, as the gas from each galaxy decelerates upon impact. Searching for these faint signatures is an immense observational challenge. But hints began to emerge from the Project Omega data. By analyzing the Doppler shifts in the absorption lines from quasars whose light passed through this critical halfway zone, astronomers could measure the velocity of the gas. They found that in the region approximately 1.3 million light-years from Andromeda, precisely where its halo should meet our own, the gas shows signs of being compressed and slowed. Its motion no longer fits the simple model of gas purely orbiting Andromeda. Instead, it seems to be responding to an external pressure. There is only one possible source for that pressure: the outward extending halo of our own Milky Way galaxy. Like two immense, invisible weather systems colliding, the halos are creating a vast boundary zone hundreds of thousands of light-years across. In this zone, gas from Andromeda, which has been coasting through space for eons, is finally encountering matter from our own cosmic shores and piling up. This discovery has far-reaching implications. The first is a slow, steady exchange of matter. For billions of years, our galaxies have been self-contained ecosystems, recycling their own gas to form new stars. Now that is changing. Gas rich in heavy elements, forged in the hearts of Andromeda's stars and blasted out by its supernovae, is now crossing a cosmic boundary and entering the gravitational domain of the Milky Way. Over millions of years, some of that Andromedan gas may cool and rain down upon our own galactic disk, providing raw material for a future generation of stars in our galaxy. A star forming in the Milky Way 500 million years from now might contain atoms of carbon and oxygen that began their journey in a different galaxy. Conversely, gas from the Milky Way's halo is now mixing with Andromeda's, destined to be incorporated into its future stellar populations. The two galaxies have begun a slow, transgalactic trade of their very substance. This halo interaction also helps to solve a long-standing astronomical puzzle: the existence of hot, metal-enriched gas clouds floating in the local intergalactic medium. For years, astronomers have detected clouds of gas between galaxies that are too hot and contain too many heavy elements. In astronomical terms, metals, to be pristine material left over from the Big Bang. Their origin was a mystery. The merging halos provide a perfect explanation. These clouds are likely the cosmic debris from this interaction. Material sloshed out and mixed together from the peripheries of both galaxies, stirred and heated by the collision of their gaseous atmospheres. We are not just witnessing the collision of two halos. We are seeing the creation of a new, shared, and chemically complex environment in the space between them. Furthermore, this revelation completely overhauls our models of how galaxy mergers work. The traditional picture was of two solid, distinct objects, the stellar disks, approaching each other and only beginning to interact when they finally made physical contact. This bowling balls model is wrong. The new paradigm shows that galaxies are not solid objects, but fuzzy, extended structures that begin to influence each other long before their bright cores get close. The gravitational and chemical interaction starts with the halos, millions or even billions of years before the main event. By the time the stellar disks of the Milky Way and Andromeda do collide, they will have been bathing in a shared, mixed atmosphere for a significant fraction of their existence. They will not be strangers meeting for the first time, but two systems that have been physically connected and influencing each other for eons. We are living in the very earliest stage of this grand merger. The word collision evokes a sudden, violent impact, But the reality is a far more gradual and stately process. It begins with this first, tentative touch of their outer atmospheres. Over the next few 100 million years, gravity will continue to pull the galaxy's cores closer, and the halos will compress further, heating up and potentially triggering new waves of star formation within the compressed gas. Only after that, billions of years in the future, will the stellar disks themselves finally interpenetrate, their beautiful spiral structures beginning to tear apart. We are at the very beginning of this cosmic timeline. The stars of Andromeda are still over 2 million light-years away, their light taking that long to reach us. But the atmosphere surrounding those stars has already bridged the gap. Even though you cannot see it or feel it, Andromeda is touching us. And what stunned researchers even more was discovering that this halo, this first point of contact, possesses its own intricate hidden structure. The ghostly halo of Andromeda is far more than a simple uniform cloud of gas. The detailed mapping from Project Omega revealed a complex and unexpected architecture. It's not a single entity, but a system of at least 2 distinct nested shells, one inside the other, each with its own unique temperature, chemical makeup, and motion. This layered structure, like the rings of a tree, encodes the history of the galaxy's life and death cycles, revealing a dynamic interplay between stellar explosions and galactic gravity that was far more intricate than anyone had predicted. The inner shell extends from the edge of the stellar disk out to a radius of approximately 500,000 light-years. The Hubble data painted a picture of this region as a place of turmoil and complexity. It is a weather zone directly influenced by the ongoing activity within the galaxy's disk. Gas velocities here are chaotic. In some areas, hot gas is clearly flowing outwards, freshly propelled by recent supernova explosions. In other regions, the data shows gas that has cooled and is now falling back inwards, drawn by Andromeda's immense gravity in a cosmic rain shower. The temperatures in this inner shell fluctuate wildly, as do the chemical abundances. It is a churning, bubbling cauldron, constantly being stirred and re-enriched by the galaxy's star-forming engine. Think of it as the galaxy's troposphere, the lowest, most active layer of its atmosphere. When a cluster of massive stars forms in one of Andromeda's spiral arms, they live fast and die young. Within a few million years, they explode as supernovae. The combined force of these explosions creates a superbubble of billion-degree gas that expands outwards. If the bubble is powerful enough, it can punch through the main gas layer of the disk and vent its hot, metal-laden contents into the inner halo. This process is happening continuously all across Andromeda's disk, creating a complex, frothy environment in the inner halo, where hot, rising plumes of new material mix with older, cooling gas that is sinking back down. The outer shell tells a completely different story. This vast region begins where the inner shell ends, around 500,000 light-years out, and extends all the way to the 2 million light-year frontier. Here, the environment is surprisingly smooth, hot, and quiescent. The gas temperature is more uniform, holding steady at a blistering 1 to 2 million degrees Celsius. The chaotic motions of the inner halo have dissipated, with most of the gas moving in a more orderly bulk flow. The chemical composition is also more evenly mixed. This outer halo is the galaxy's stratosphere, a more ancient and settled layer. It is composed of material that was ejected from the galactic disk, not millions, but hundreds of millions, or even billions of years ago. Over these immense timescales, the initial violence of its expulsion has faded. The gas has had time to expand, cool slightly, and mix thoroughly with its surroundings, erasing the clumpy, turbulent signatures that still characterize the inner shell. It represents the accumulated exhaust of countless generations of stars, a vast reservoir of recycled matter waiting to eventually cool and participate in the galactic fountain cycle. The boundary between these two shells is not a sharp line, but a gradual transition zone tens of thousands of light years thick. In this region, the properties of the gas blend from one regime to the other, suggesting a continuous and ongoing exchange of matter and energy between the shells. Hot gas from the inner shell is constantly flowing outward to replenish the outer halo, while gas in the outer halo that radiates away enough energy can cool and sink downwards, eventually rejoining the inner halo. The discovery of this layered structure was a genuine surprise. Most theoretical models and computer simulations of galaxy formation had produced halos with much smoother, more uniform properties. They failed to capture this distinct, two-part architecture. The discrepancy suggests that our models of supernova feedback, the process by which exploding stars inject energy and matter into the halo, are still too simplistic. The universe is proving to be more complex and structured than our simulations had allowed. Some of the most powerful evidence for this model comes from a detailed chemical analysis of the heavy elements within each shell. All elements heavier than hydrogen and helium are forged inside stars and can only get into the halo by being violently expelled. By measuring the relative amounts of different elements, astronomers can perform a kind of cosmic archaeology. For example, the inner shell shows a high abundance of oxygen and silicon relative to iron. These alpha elements are preferentially produced in massive stars that explode as core collapse supernovae just a few million years after they form. Their strong presence in the inner halo is a clear signature of recent contamination from Andromeda's active star-forming regions. The outer shell, in contrast, shows a slightly different chemical pattern with a higher proportion of iron relative to oxygen. Iron is predominantly created in a different type of explosion called a type Ia supernova. These occur when small, dense stellar remnants called white dwarfs accrete material from a companion star and explode. This process happens on much longer timescales, over billions of years. The chemical signature of the outer halo thus points to it being older material, enriched by many different generations of stellar evolution over a vast span of cosmic time. This complex layered structure makes the impending merger with the Milky Way an even more intricate affair. The halos will not collide as simple uniform spheres. The turbulent inner shells will likely interact first, creating a zone of intense shock heating and compression. The vast, hot outer shells will then press against each other, creating an even larger and hotter interaction region. Understanding this structure is key to predicting the detailed timeline and consequences of the merger, from future star formation rates to the final structure of the combined galaxy. The halo is a critical component of Andromeda, containing as much mass as half its stars, but it is only one part of the galaxy's total mass budget, 1 trillion stars. The number is so vast it borders on the incomprehensible. If you were to start counting them, 1 star per second, it would take you nearly 32,000 years to finish. Andromeda contains enough suns to give every single human being who has ever lived on this planet their own personal fleet of over 10,000 stars. This colossal stellar population, which outnumbers the stars in our own Milky Way by a factor of at least 3 to 1, is the luminous heart of the Andromeda Galaxy, and its immense collective mass is the primary anchor for the even more massive structures surrounding it. These stars are not spread out uniformly. Their density varies by orders of magnitude, from the hyper-congested core to the sparse, lonely frontiers of the outer disk. In the central bulge, a brilliant yellowish sphere of old stars at the galaxy's heart, the stellar crowding is extreme. If Earth orbited a star in Andromeda's core, our night sky would be a terrifyingly brilliant spectacle. Thousands of stars would blaze with a brightness greater than Venus at its peak, and the combined starlight from the dense stellar field would be intense enough to cast distinct shadows on the ground at midnight. There would be no true darkness. Moving outward into the grand spiral arms, the stellar density decreases but remains significantly higher than in the Milky Way's suburbs where we reside. These majestic arms, traced by glowing dust lanes and nebulae, are the galaxy's stellar nurseries. They are home to massive clouds of cold molecular gas, the raw material from which new stars are constantly being born. These regions are alight with the brilliant blue-white glare of young, hot, massive stars. A single one of these star-forming complexes, like the famous NGC 206 visible in telescopes, can give birth to thousands of new suns in just a few million years, a furious pace of creation that helps sustain the galaxy's stellar population. The spiral arms themselves are not physical structures like a pinwheel's arms. They are density waves, slowly rotating patterns of gravitational compression that sweep through the disk. As stars in their individual orbits encounter one of these waves, they are temporarily slowed and bunched together, creating a region of higher density and triggering the collapse of gas clouds to form new stars. The stars themselves pass through the wave and continue on their orbits, much like cars passing through a temporary traffic slowdown on a highway. Between the arms lie the vast, dimmer inter-arm regions. Here, the stellar population is older, dominated by yellow and red stars like our Sun, or smaller, long-lived red dwarfs. These stars were born in the spiral arms billions of years ago and have since drifted out into more solitary orbits. They represent the bulk of Andromeda's stellar mass, the quiet, stable citizenry of the galaxy that will continue to shine for trillions of years, long after the brilliant but fleeting blue giants have exhausted their fuel and vanished. In addition to these luminous stars, Andromeda is also home to hundreds of billions of failed stars known as brown dwarfs. These objects formed from collapsing gas clouds, just like stars, but they never accumulated enough mass, about 8% of our Sun's mass, to ignite sustained hydrogen fusion in their cores. They glow faintly in the infrared, slowly radiating away the heat of their formation. While they contribute almost nothing to the galaxy's light, their collective mass is significant and must be accounted for in any total mass calculation. The variety of stars mirrors what we see in our own galaxy, but on a grander scale. Red dwarfs are by far the most numerous faint embers that will outlive every other object. At the other extreme, rare but spectacular blue supergiants burn through their fuel in a cosmic heartbeat of a few million years, ending their lives in cataclysmic supernova explosions that forge and distribute the heavy elements essential for life. Binary star systems are ubiquitous, with pairs or even groups of stars locked in intricate gravitational dances. Some orbit so closely that they exchange material, leading to exotic phenomena like X-ray binaries, where matter from a normal star is siphoned onto a neutron star or black hole, or type 1a supernovae. the explosions of white dwarfs that have grown too massive, and orbiting a vast fraction of these 1 trillion stars are planets. If the planet-to-star ratio in Andromeda is similar to our own galaxies, and there's no reason to think it isn't, then there are likely trillions of worlds circling those distant suns. Rocky worlds, gas giants, ice worlds, and forms of planets we have yet to discover. Across such a vast sample size, the existence of worlds with liquid water and the right conditions for life seems not just possible, but probable. Somewhere in that faint smudge of light, other civilizations could be looking back at us, wondering about the faint spiral galaxy they call the Milky Way. Counting these stars is an impossible task. Instead, astronomers estimate the total population by measuring the galaxy's total light output and modeling its stellar populations. The monumental panchromatic Hubble-Andromeda Treasury FAT program created an unprecedented mosaic of the galaxy, resolving over 100 million individual stars in its disk and halo. Even this incredible feat captured only about 10% of the total population, with the rest either lost in the glare of the core or too faint and distant to be resolved. This stellar census is crucial as it provides the baryonic, normal matter, mass baseline for the galaxy. But the stars, for all their glory, are just the tip of the iceberg. The new measurements of the halo revealed a component of normal matter that was just as, if not more, massive. Adding the 500 billion solar masses of gas in the halo to the estimated 1.5 trillion solar masses of stars in the disk brings Andromeda's total baryonic mass to a staggering 2 trillion solar masses. And even that colossal number is dwarfed by the galaxy's dark matter component, which likely accounts for 85 to 90% of its total mass. The true mass of Andromeda, the number that dictates its gravitational power and its ultimate fate, is likely closer to 15 trillion solar masses. This new, heavier Andromeda is a much more formidable dance partner for the Milky Way, changing all predictions about their future. But this revelation of mass only came after astronomers first learned to measure motion. For over a century, we have known that Andromeda is hurtling towards us. The speed of its relentless approach is 110 kilometers per second. This translates to roughly 400,000 kilometers per hour, or about 250,000 miles per hour. At this velocity, you could travel from New York to Los Angeles in just 36 seconds. You could circumnavigate the Earth at the equator in under 6 minutes. It is a speed that is fantastically high by any human standard. Yet when set against the colossal 2.5 million light-year gulf separating our galaxies, it appears almost glacial. At this rate, the journey will still take billions of years to complete. The measurement of this speed is a cornerstone of modern cosmology and represents a remarkable story of scientific discovery, refinement, and the gradual peeling back of cosmic illusions. The first clue came in 1912, long before we even knew that spiral nebulae were other galaxies. The American astronomer Vesto Slipher, working at the Lowell Observatory in Arizona, was painstakingly capturing the spectra of these faint, fuzzy patches. When he developed the photographic plate for Andromeda, he saw something that defied all expectations. The characteristic dark absorption lines in the spectrum, which act as cosmic barcodes for elements, were not in their expected positions. They were all shifted towards the blue end of the spectrum. This blue shift was the unmistakable signature of the Doppler effect, indicating an object moving towards the observer at a tremendous speed. Slipher's initial calculation put Andromeda's approach velocity at a stunning 300 kilometers per second. This finding was deeply puzzling. At the time, Edwin Hubble had not yet made his definitive discovery that the universe was expanding. But even within the static universe model, Slipher was finding that almost every other nebula he studied was redshifted, moving away from us. Andromeda was the glaring exception, and its high velocity seemed incompatible with the idea that it was a simple gas cloud within our own Milky Way. Slipher's measurement was a monumental achievement, but it contained a subtle error, not of his own making, but because he couldn't account for our own motion. The velocity he measured was relative to his telescope in Arizona, but that telescope is on a planet that is rotating, orbiting a star, and that star is itself hurtling through the galaxy. We are not stationary observers. Our entire solar system is orbiting the center of the Milky Way at a breathtaking speed of about 220 kilometers per second, nearly 500,000 miles per hour. To find Andromeda's true velocity relative to the Milky Way as a whole, astronomers had to perform a complex series of subtractions. They had to calculate the sun's velocity vector and subtract it from Slipher's observed value. It's like trying to measure the speed of an oncoming train while you yourself are on a different train, moving on a curved track. You have to know your own speed and direction perfectly to deduce the other train's true speed. Over the decades, as our measurements of the sun's motion around the galaxy became more and more precise, the calculation for Andromeda's approach was refined. The final corrected value settled at the now accepted figure of 110 kilometers per second. This velocity tells us something profound about our place in the universe. In a cosmos where space itself is expanding and pushing almost all distant galaxies away from each other, the fact that Andromeda is approaching means that the gravitational attraction between it and the Milky Way is powerful enough to overcome that cosmic expansion. We are not just two random galaxies passing in the cosmic night. We are the two dominant members of a gravitationally bound family of over 80 galaxies known as the Local Group. Within this group, the Milky Way and Andromeda are the cosmic patriarch and matriarch. Their immense combined gravity dictating the motions of all the smaller dwarf galaxies that orbit them. Their inward fall towards each other is an inevitable consequence of gravity, acting over billions of years within this shared cosmic habitat. This approach velocity is the engine of the future merger. It is the number that sets the fundamental timescale for the collision. But by itself, it is incomplete. The 110 kilometers per second figure only represents the radial velocity, the component of motion directly along our line of sight. It tells us how fast Andromeda is getting closer, but it tells us nothing about its tangential or proper motion, its sideways drift across our line of sight. Imagine two people running towards each other in a field. Knowing only how fast their separation is decreasing doesn't tell you if they are on a direct collision course, or if they will run right past each other. To know that, you need to know their sideways motion as well. For galaxies, this sideways motion is the critical missing piece of the puzzle, the one that determines whether the future holds a cataclysmic head-on collision, a glancing blow, or a near miss. Measuring that tiny, almost imperceptible sideways drift for an object 2.5 million light-years away would prove to be one of the greatest observational challenges in the history of astronomy. Measuring the sideways motion of an object 2.5 million light-years away is an act of almost unbelievable precision. It is the observational equivalent of standing in New York City and trying to detect the width of a human hair moving in Los Angeles. This tiny, almost imperceptible drift across the sky, known as proper motion, is the single most important variable needed to predict Andromeda's future trajectory. Without it, we know the car is speeding towards us, but we have no idea which lane it is in. It is the key that unlocks the geometry of the collision, transforming the forecast from a vague premonition into a detailed simulation of our cosmic destiny. Proper motion is measured in angular units on the sky, typically in milliarc seconds per year. An arc second is 1/36th of a degree. A milliarc second is 1,000th of that. To put this in perspective, the full moon spans about 1,800 arc seconds. The angular motion we are trying to detect for Andromeda is a minuscule fraction of that. If Andromeda had a sideways velocity comparable to its approach velocity of 110 kilometers per second, its proper motion would be just 0.009 milliarc seconds per year. Detecting such an infinitesimal shift was far beyond the capabilities of any telescope for most of the 20th century. The challenge was finally met by the one instrument capable of the task, the Hubble Space Telescope. Floating above the distorting blur of Earth's atmosphere, Hubble can achieve extraordinary angular resolution, allowing it to pinpoint the positions of stars with unprecedented accuracy. A team of astronomers, led by Roland van der Marel at the Space Telescope Science Institute, devised a brilliant and patient experiment to nail down this critical measurement once and for all. The principle was simple, but the execution was immensely complex. They used Hubble to take hyper-precise images of several small regions within Andromeda. Then, they waited. They came back and re-imaged the exact same fields of view between 7 and 8 years later. By comparing the before and after pictures, they could look for a systematic shift in the positions of the Andromeda stars relative to the background. The key to the experiment was distinguishing Andromeda's motion from other effects. The positions of the stars on Hubble's detector could be affected by tiny changes in the telescope's orbit or temperature. The solution was to use a fixed external reference frame. Fortunately, scattered across the images, far behind Andromeda, were a handful of incredibly distant galaxies and quasars. These objects are billions of light-years away, so distant that over a mere 8-year period, their apparent motion on the sky is effectively zero. The team's task was to measure how the entire field of Andromeda stars in their images had moved, as a group, relative to these stationary background objects. They measured the positions of thousands of individual stars in each field in both sets of images, a process requiring intensely sophisticated software to disentangle the crowded star fields. By averaging the tiny shifts of all these stars, they could cancel out random errors and isolate the minuscule collective drift of the Andromeda Galaxy itself. The results, announced in 2012, were a landmark in observational cosmology. They had successfully measured Andromeda's proper motion. The numbers were tiny, just as predicted. They found a sideways motion of about 0.017 milliarc seconds per year in a southerly direction, and about minus 0.015 milliarc seconds per year in a westerly direction on the sky. When these angular motions were translated into physical velocities at Andromeda's distance, the result was stunning. The tangential, or sideways, speed of Andromeda relative to the Milky Way was found to be very small, less than 50 kilometers per second. This was significantly smaller than the 110 kilometers per second approach velocity. The implication was clear and inescapable. Andromeda is not heading for a near miss. It is not going to slide past us. It is heading almost directly for us. The car is, in fact, in our lane. The measurement, while groundbreaking, still carries uncertainties. The error bars on the velocity measurement are around 30 kilometers per second. This means the true sideways speed could be anywhere from nearly 0 to about 80 kilometers per second. While this range is small enough to confirm that a collision is the most likely outcome, this remaining uncertainty has enormous consequences for the type of collision we can expect. A very low tangential velocity would lead to an almost perfectly head-on impact, a scenario of maximum violence and disruption. A slightly higher tangential velocity at the upper end of the uncertainty range would result in a glancing blow or an off-center collision. Over a 4 billion-year journey, a sideways velocity of just 50 kilometers per second translates to a lateral displacement of over 650,000 light-years. This is more than the diameter of either galaxy's stellar disk. The difference between a head-on crash and a sideswipe that misses the galactic cores on the first pass is hidden within those error bars. This single heroic measurement changed the collision from a possibility into a near certainty. It provided the final critical input parameter needed for supercomputer simulations to model the future interaction in detail. By combining the known masses, distances, radial velocity, and now the tangential velocity, physicists could finally run the clock forward and watch the cosmic dance unfold. The measurement of Andromeda's lateral motion stands as a testament to scientific patience and ingenuity. It is a number derived from a shift on a digital detector smaller than anyone had ever reliably measured before, yet it holds the key to the fate of two of the largest structures in our corner of the universe. For a time, the future seemed settled. With the measurement of Andromeda's sideways motion confirming a collision course, the question shifted from if to when. Supercomputer simulations, now fed with all the key parameters, converged on a dramatic timeline. First contact in about 4 billion years, with the two galaxies fully merging into a new, single entity a few billion years after that. The fate of the Milky Way seemed written in the stars, but the universe is rarely so simple. Just as one source of uncertainty was resolved, a new, far more complex one emerged. The initial models, for all their sophistication, had treated the problem as a simple two-body interaction. Just the Milky Way and Andromeda falling towards each other. The reality is that we live in a crowded neighborhood, and the gravitational influence of the other residents of the local group, previously dismissed as negligible, turns out to be a powerful agent of chaos. This realization has dramatically shifted the forecast, dropping the probability of a merger from a near certainty to something much more ambiguous, a 50-50 coin flip. The game changer was the flood of ultra-precise data from the European Space Agency's Gaia spacecraft. Launched in 2013, Gaia's mission is to create the most accurate and extensive three-dimensional map of our galaxy ever made by measuring the positions, motions, and distances of billions of stars. This data also includes precise measurements for stars in nearby galaxies, allowing astronomers to trace their orbits with unprecedented fidelity. A team of astronomers led by Chitske Pichlu and Avi Loeb used this new Gaia data to build the most comprehensive simulation of the local group's future dynamics ever attempted. They didn't just model the Milky Way and Andromeda. They included the third largest member of the group, the Triangulum Galaxy, M33, as well as our own largest satellite galaxies, the Large and Small Magellanic Clouds. They ran thousands of simulations, each time tweaking the initial masses and velocities of these galaxies within the tiny uncertainties of the new data. This statistical approach, known as a Monte Carlo simulation, doesn't produce a single future. It produces a spectrum of possible futures and their probabilities. The results were a bombshell. When they ran the simulations with just the Milky Way and Andromeda, they found a collision probability of less than 50%, already lower than the consensus, suggesting that even small uncertainties in the initial conditions could lead to a near miss. The real surprise came when they added the other galaxies, including the Triangulum Galaxy, which may be a gravitational satellite of Andromeda, actually increased the odds of a merger to about 67%. Its extra mass, located roughly between the two giants, acts as a bit of extra gravitational glue, helping to ensure they connect. But the final and most crucial ingredient was the Large Magellanic Cloud, LMC. This dwarf galaxy, visible from the southern hemisphere, is much more massive than previously thought and is currently on its first ever dive towards the Milky Way. It is destined to merge with our galaxy in about 2.5 billion years, well before Andromeda is scheduled to arrive. The Gaia data allowed the team to model the LMC's orbit and its impending merger with our galaxy with high precision. When they factored in this future collision, the probability of a subsequent Milky Way-Andromeda merger plummeted back down to 50%. The reason is that the LMC's merger will act like a powerful gravitational shove to the Milky Way. It will transfer a huge amount of momentum to our galaxy, significantly altering our trajectory through the local group. Depending on the exact angle and timing of the LMC's impact, that shove could either nudge us more directly into Andromeda's path or, just as likely, deflect us enough to cause us to miss. With the current uncertainties, both outcomes are equally possible. Our galaxy's fate is tied to a cosmic game of billiards, and the balls are still in motion. This has profound philosophical implications. We are used to thinking of the cosmos in deterministic terms, governed by Newton's unwavering laws. But this work reveals that on the grandest scales, the universe is subject to chaotic dynamics. In a chaotic system, tiny, imperceptible differences in initial conditions can lead to wildly divergent outcomes over long periods. The future of our local group is not a pre-written script. It is a branching set of possibilities, exquisitely sensitive to the precise starting positions and velocities of its members, values we can never measure with infinite perfection. We have moved from the realm of celestial mechanics to celestial statistics. We can no longer say with confidence, the Milky Way will collide with Andromeda in 4 billion years. The honest scientific statement is now, there is a roughly 50% chance that the Milky Way will merge with Andromeda within the next 10 billion years, and the timing of that potential merger is itself highly uncertain. This uncertainty is not a failure of science. It is a more advanced and honest reflection of reality. It acknowledges the complexity of the system and the inherent limits of prediction over cosmic timescales. Future data from Gaia and other observatories will continue to shrink the error bars on these measurements. And as they do, the probability will likely shift away from 50-50, perhaps moving towards 70% or down to 30%. We may get a clearer picture, but some level of fundamental uncertainty, rooted in the system's chaotic nature, will likely always remain. The coin is still in the air, The ultimate destiny of 1 trillion stars and our own distant descendants hangs on which way it lands. This uncertainty forces us to consider two starkly different futures for our cosmic home. We stand at a profound fork in cosmic time, faced with two dramatically different destinies for our home galaxy. The 50% probability is not just a number, it is a gateway to two separate futures. In one, the collision occurs, and the grand spiral structures of the Milky Way and Andromeda are utterly destroyed to give birth to a new, colossal elliptical galaxy, a celestial behemoth already nicknamed Milkomeda. In the other future, the galaxies execute a gravitational near miss, a close pass that will still wreak havoc, but will leave both galaxies as separate, albeit scarred, spiral entities for billions of years to come. Both scenarios represent a fundamental transformation of our local universe. Let's first explore the future of the collision, the birth of Milkomeda. Should the galaxies merge, the process will be a slow-motion cataclysm, spanning hundreds of millions of years. Despite the immense number of stars, direct stellar collisions will be virtually non-existent. The space between stars is so vast that the two galaxies will mostly pass through each other like ghosts. The real action will be driven by gravity and gas. As the galaxies interpenetrate, their mutual gravitational pull will throw stars out of their orderly, circular orbits. Powerful tidal forces will stretch the galactic disks, drawing out immense streamers of stars and gas known as tidal tails, which will arc across hundreds of thousands of light-years of space. For any observers present, the sky would become a spectacular, terrifying canvas of sweeping stellar rivers and distorted galactic cores. The gas clouds of the two galaxies, however, will not pass through each other. They will collide head-on, creating massive shock waves that compress the gas and trigger a furious burst of star formation, a starburst. For a period of about 100 to 200 million years, the merging system will blaze with the brilliant blue light of millions of newborn massive stars. The rate of star formation could increase by a factor of 100 or more, rapidly consuming the available gas reservoirs. After several passes and oscillations, the two galactic cores, with their supermassive black holes, will finally spiral together and merge. Andromeda's central black hole, weighing in at around 140 million solar masses, will swallow the Milky Way's comparatively modest 4.3 million solar mass black hole. This event will unleash an almost unimaginable burst of energy in the form of gravitational waves, a ripple in the fabric of space-time that will radiate across the universe. The end product of this violent process, taking roughly 2 billion years from first contact to final settlement, will be Milkomeda. It will be a giant elliptical galaxy, a smooth, featureless, three-dimensional swarm of around 1.3 trillion stars. All traces of the beautiful spiral arms will be gone, replaced by a chaotic jumble of stars on random elliptical orbits. Having exhausted most of its cold gas in the merger-induced starburst, Milkomeda will be a red and dead galaxy. Star formation will grind to a halt. Its stellar population will simply age, the galaxy slowly fading in brightness from blue-white to a dull, ruddy yellow-orange over the subsequent eons as its remaining stars evolve and die without replacement. Our sun will still exist during this transformation, but its own evolution into a red giant will have already rendered Earth uninhabitable long before the final merger. Our solar system itself has a non-zero chance, perhaps 12%, of being flung out of the new galaxy entirely during the chaos, destined to become a rogue system, wandering the lonely void of intergalactic space. Now consider the other future, the 50% chance of a near miss. In this scenario, the galaxy's tangential velocities are just high enough that their cores do not collide on the first pass. Instead, they will swing past each other at a distance of tens of thousands of light years. This would not be a gentle event. The gravitational encounter would still be powerful enough to severely distort both galaxies. Long tidal tails would still be drawn out, and bridges of gas and stars might form, temporarily connecting the two systems. The outer regions of both disks would be irrevocably scrambled, and the encounter would likely trigger significant, though perhaps less intense, bursts of star formation. After the first close pass, the galaxies would continue on their paths, moving apart again. However, their mutual gravity would have robbed them of orbital energy, ensuring they are still bound to each other. They would slow down, reach a maximum separation, and then inevitably begin to fall back towards each other for a second encounter, perhaps hundreds of millions or even a billion years later. This cosmic dance could continue for several passes, a series of progressively closer and more disruptive glancing blows, before they eventually lose enough energy to finally merge. A near miss, therefore, doesn't necessarily avoid a merger indefinitely. It just delays it, potentially for billions of years, and changes the nature of the interaction from a single violent crash into a prolonged, grinding process of mutual harassment. For a future civilization living in the Milky Way, this scenario would be profoundly different. Instead of their home galaxy being destroyed, they would witness its periodic, violent interactions with a colossal neighbor that would dominate their sky during each close approach. They would live in a spiral galaxy, but one with a permanently scarred and distorted outer disk, a constant reminder of its turbulent relationship with Andromeda. The long-term survival of the spiral structures makes this a less definitive, more dynamic future. Both scenarios represent a point of no return. Whether through a single, swift merger or a long series of glancing blows, the local group as we know it is destined for consolidation. The era of two dominant, separate spiral galaxies is drawing to a close, one way or another. The new measurements of Andromeda's true size, its massive halo, its violent past, and its uncertain trajectory have transformed our cosmic forecast. We are no longer passive observers of a distant, static universe. We are residents of a dynamic, evolving system caught in the gravitational cross-currents of giants. We look at that faint, fuzzy patch in the night sky, not just with wonder, but with a new sense of profound connection and trepidation. The journey from a small cloud to a monster already touching our shores is a testament to the power of scientific inquiry. We have unmasked a galaxy far larger, more massive, and more complex than we ever dreamed. Its 220,000 light-year stellar disk is a mere bright spot within a 2 million light-year halo, a structure so vast it has already begun to merge with our own. This invisible giant, containing the mass of 500 billion suns in its gaseous atmosphere alone, is hurtling towards us at 110 kilometers per second. Yet for all this knowledge, our ultimate destiny hangs in the balance. The subtle sideways drift of this behemoth, a motion so small it challenges the very limits of our technology, is the deciding factor. It is the variable that transforms a certain collision into a 50-50 probability, a cosmic coin flip. Will our Milky Way be consumed in a fiery merger, reborn as part of the colossal elliptical galaxy Milkomeda? Or will we engage in a multi-billion-year gravitational dance of near misses, our familiar spiral home scarred and distorted but surviving? We cannot yet know the answer. We live in a moment of profound cosmic uncertainty, armed with enough knowledge to ask the question, but not quite enough to answer it definitively. We can only continue to watch, to measure, and to refine our understanding of the forces that govern our fate. The story of Andromeda is a humbling reminder that the universe we see is but a pale shadow of the universe that is. Hidden in the darkness are structures of unimaginable scale and processes of unimaginable power, all unfolding on timescales that dwarf human existence. The monster in our sky is real. Its approach is relentless, and its story is our own.